Hello everybody, today we'll be doing accounts merge. Given a list of accounts where each element, account I, is a list of strings where the first element, account I at 0, is a name and the rest of the elements are emails representing emails of the account. Now we would like to merge these accounts. Two accounts definitely belong to the same person if there is some common email to both accounts. Note that even if two accounts have the same name and they may belong to different people, as people could have the same name. A person can have any number of accounts initially, but all of their accounts definitely have the same name. After merging the accounts, return the accounts in the following format. The first element of each account is the name, and the rest of the elements are emails in sorted order. The accounts themselves can be returned in any order. Okay, let's take a look at the first example to understand what they're talking about. Here we are given a bunch of accounts, and we have one John here, we have two Johns here, we have one Mary here, and another John here, and we have a total of 4 accounts currently. And in our output, what we have here is one John here, one Mary here, and another John here. And see, as you can see, there has been a merge that occurred between John, these two emails, and we completed by creating this brand new concatenated account with all the emails. So what are some edge cases that we can think about at this point? Like, what if they don't have an email? Is that possible? Well, let's take a look at some of the constraints. And first things first, there can be only the minimum is 1 account. That means that there must be at least 1 account here. And this means that, let's delete this. This is an edge case. Essentially, there's one thing, and there can only be one thing returned. Next, account I length must be between 2 and 10. So basically, the maximum number of emails that are possible are a total of 9 emails. So a maximum of 9 emails. We can copy like some of this stuff here, maybe, and just tack it on, like, right, and so on and so forth. So 10 emails, right? And of course, they can grow to be much longer in this section here. So something like this. And the length of each character here is a maximum between 1 and 30 characters. So it cannot be 0 characters. It must be at least 1 character long, all the way up until not 30 characters long. With that, J of 0 is English characters, and all of these items are valid emails. We don't have to check for them as valid or invalid emails. So we can be content with that. And with that, I think we're good with our edge case. Let's think about like time and space complexity, that what we want to do in this case. How do we even consider this? So time and space complexity, I'm looking at going through at least every single account, n for each account, and k for each email in each account, right? So n times k at the very least. And there's also a sorting that needs to be done. So if we took all the emails from all the accounts and we sort them, we're going to take a nk log nk. So that's our max. Oh, that's what we're looking at. Log nk for sorting. So our total time complexity is O of n k log nk. Okay, so here's the space-time complexity. What the space-time complexity is going to be n times k, because for each account and for each email, even though they're in sorted order, it doesn't take more space to store sorted things. So that's our intended time and space complexity. So just need to move that over here, and we're good to go. So O of nk. Perfect. With that, I think we can talk about the match. And the match that we're going to do is that we're going to create graphs emails. And by creating a graph of emails, we can connect all of these emails together. And with a connection, we can say, oh, we have connected all these emails together. That means they're from one user, and we can eliminate them from the pot of emails. So here's what I mean. Suppose we have this John here, right? We create a set of emails. So we have one here. We have another here, right? We point it back that way. We point it this way. We point it every which way, all right? So this is a graph. We can point it 100 directions. Yeah, can be a different 100 emails. No problem. So now we have we found this similar email, and so we're going to point this item to this new item, next item here, as you can see. So with those pointing to each other, we can see that all of these items are connected. We can say, oh, this all belongs to John, right? Of course, this means we need a email to name item dictionary to make this happen for us. And this is a graph, and we're looking at these nodes called emails, and they're connected to other nodes of emails. And so with this, this Mary is not connected to anything, and this Johnny Bravo is also not connected to anything. With that, they'll be separated from each other. And so basically, our plan is pretty simple. So let me write out my plan here, since everything has disappeared. So our plan is to create a graph between related emails, create a email to name dictionary, and we also need to make sure to eliminate all visited nodes and assign one round of visited nodes to a result, a single name, to be appended to the output. And that's it. That's our plan. Pretty simple plan. Doesn't seem too difficult. And let's get to it. So first things first, we're going to create a graph. So the graph is going to be a default dict of sets. So we're going to have a key that is going to be our email, and it's going to be point to a set of emails, like so. And that way, they are connected, and all there are cycles, but we can eliminate that with using visited set. So what's next? We also need an email to name dictionary, and that will hold the email to our name, which we need to create. So let's start creating. So for account, in accounts, for email, in accounts, from 1 to the end. And let's make those emails. So graph at the email is equal to dot add this account at I at 1, and what we're gonna do is graph at account at 1 is going to be dot add. We're gonna add that email, all those emails. Of course, 1 is related to itself, so that's not a problem. With that, let's finish this off with the email name. So, so for the count, so email to name is equal to, at this particular account at 0, at 1 is equal to account at 0, which is the name. So do we want to be more specific? We can. Just give me a little bit of time. So name is account equal to account at 0, and we're going to set that as the name. Email account 1 is our email. our first email is equal to count 1. So I think by doing this, it will be a little bit clearer. I think that we should do this here instead. So first email is account 1. Email to name. Name is going to be account 0. I like that. I like that a lot. And we can do a for loop for all the other emails and add the first email to all of these right here, and that will clean up our code a little bit and make it look nice to look at. So that's important. So for the next reader to know what's going on. For each account, they know exactly what we're doing, and we're looking at all other emails when they read this code. I need a drink of water. So I'm going to... All right, let's take a look at our next step, which is eliminating all visited nodes and assigning everything to one round. How we're going to do that is that we're going to create a visited set of items. They're called visited emails. We're no longer visiting them anymore. And we're going to do this by visiting every single node, by visiting all associate nodes. To do that, we're going to do for each email in the graph. Well, what happens here is that we look at the email, and we're going to put in a stack. So stack is equal to email. And because we put it into the email, we must say check if it's not in visited. Because if it's been visited, we don't want to visit it again and waste our time, right? So if the email is not in visited, stack is equal to visit email, visited dot add email. So those two steps must be done. And we're going to visit all the related emails. So for graph, so while stack, right? So node is equal to stack.pop. We're going to pop this email out and call it a node. So for graph at this node, so these are all the edges of this graph. And what's going to happen is that if edge not in visited, that means they haven't been visited. What we're going to do now is check all of them. So visited dot add edge and stack dot append the edge. And so we're going to keep doing this until we have visited every single item that is connected to this edge. And we're going to keep going. Like if this John Smith, we put that in. We take a look at the edges. So these are two edges that are in our stack now. And if they have edges, they will also append items to the edge, and they would be marked as visited. And so on and so forth. We're doing a DFS, and we are going to visit every single associated node, or associated node essentially, and put it into our visited set. And when we do that, what we want to do is that let's create a local results, which is empty array, and let's add each node. Every single time we see a node, let's add that to our, let's append that node. That node is just a string, and so we're going to keep appending these emails basically into our local result every time. So we append to every single visited item, as we've said. Eliminate all visited nodes and assign one round of visited nodes to a single name to be appended to the output. So exactly as we have suggested here. We have not appended to our results or output. So output is going to be set to empty array, and we're going to we basically compiled all the emails. So output dot append for this one email, we need an email to name, and we need to turn this into an array. So email to name at this email is going to do an add of our local results. And we need to also remember that we need to keep this in sorted order. So which needs to be in sorted order. So let's make sure that happens because if it's not sorted, it's not right. So let's sort. And perfect. There we go. That's the output. So for every email, we'll create this output if the email is not invisited. Let's move this right here because if it isn't visited, if it's in the visited, we don't want to add that to our results anymore, right? Only if it has not been seen. So then we add it to output. With that, our output is ready to go, and let's return the output. With that, I believe that we are good to go. We followed all the orders as expected. Let's make sure if this time complexity is good. So let's comment all of this out. The reason for that is because we can't run the code if we don't comment it out. And let's do evaluate afterwards, which is this is the expected evaluation. Let's run the code, see if it works. If it doesn't, let's go fix the code if it's missing anything. Looks like it's accepted, so let's run all the example test cases. And everything's good, so let's check out that solution. Perfect, wow, very fast solution. And it looks good to go. What we need to do now is go over the evaluation. And as evaluated, we spent this top part is n times k because we went over all the accounts, and for each account we went over all the emails. That's going to be nk space to create this graph. Also, it's going to plus n for number of items inside our emails to name, but the overall it's n times k for the time and space here at this point. As we go down, we're going to visit every single email in the graph as you see here for each email, and each email is connected to all the other emails in the stack. So we're going to visit nk again. Once we have all the items put aside into one single item, we're going to do a sort on that n times k items. We're going to basically run nk items here, max total. Basically, we're going to add until we have nk and sort all of those. Basically, it's nk log nk for the sorting. And that's how we get our time. And space-wise, yes, it's just for the graph. With that, we have solved the problem within our time constraint, and we have gotten a pretty great answer. And the way that we did that was that we created a graph, we visited all the nodes in the graph, and we assigned all those visited nodes into a single result, and we sorted, and we created our we appended that local result to output, every single for each individual node that's not connected, that's not associated, and we were able to create our outputs. With that, I hope you enjoyed this video and you learned something. If you have code that you would like to share that makes this code even better, ways that makes better, let's all learn together, and please post a comment. If you enjoyed this video, like and subscribe. If you want more videos, check the link in the description below. Thank you very much, and I will see you in the next one.